Hey guys, welcome to Unit 10 Notes B. Today we're going to talk about equilibrium, chemical equilibrium to be exact, or an equilibrium that's reached during a chemical reaction. Not all chemical reactions go one way. Reactants do combine to form products, but sometimes those products can recombine to turn into reactants. So when we have this, we call it a reversible reaction, and we would indicate that with a two-way arrow, showing that A and B combine to form C and D, but then also C and D can go backwards to remake A and B, this reversible reaction. And this is your typical format for expressing a reversible reaction. When we look at the equilibrium expression, we're going to use these letters to kind of show where things go. So the lowercase letters here would be the coefficients, and the capital letters would be the chemicals themselves. And then in between reactants and products, you have that two-way arrow. So let's look at what happens to the rates of equilibrium rates of a chemical reaction at equilibrium. Well, one reaction would be where A and B were combining to form D. The other reaction would be where C and D are recombining to form A. We would call those the forward reactions and the reverse reactions. The forward reactions would be where A plus B makes C and D. Whereas the reverse reaction would be where C and D are going back to form A and B. Now, when a chemical reaction starts out, there aren't any C or D molecules. So the rate of C and D recombining starts at 0 because there are no products to work backwards from. As we make more and more products, this rate will increase. On the flip side, A and B are going to be combining to form C and D at maximum rate when it very first starts. But then as A and B are used up, that rate will slow down. When you reach the point where those rates become equal to each other, you reach something called equilibrium. And we would stay at equilibrium as long as those rates are equal to each other. So from this graph, we have half of our definition for equilibrium. The rates of the forward and reverse reaction must be equal at equilibrium. Now let's look at the concentrations. The red would indicate the reactants, and when you very first start the reaction, you would have 100% reactants, and those would be slowly used up. Then you would have products starting at 0, because you never have product when you first start the reaction. But as product is formed, its concentration would increase. And we do have a reversible reaction here, so we can see that B is coming back to form A in this situation. So A is not going to bottom out, but it is going to become level. So this point here, where the amount of product and the amount of reactant become level, showing that the concentrations stay constant, will occur at equilibrium. So this is the other half of our definition for equilibrium. The concentrations remain constant at equilibrium. So chemical equilibrium occurs whenever you have equal rates and constant concentrations. Quick little side note, that reaction would stay at equilibrium as long as the system is closed. But if you introduce new things into a system, if you change the conditions, your system would shift to change to a different equilibrium. So we call this a closed system. So within a closed system, once you reach equilibrium, you would continue to stay at a point where the rates are equal and the concentrations are constant. Equal rate, constant concentration. Basically a four-word definition to establish chemical equilibrium. Now, chemical equilibrium is what we call a dynamic equilibrium, or a moving and changing equilibrium. It may look as if nothing is happening because the concentrations don't change. So it looks like you have the same amount of reactants and products once you reach equilibrium. But if you zoom into that molecular level, the reactants are turning into products and the products are turning into reactants. There is a constant breaking and forming of bonds going back and forth, a chemical change occurring in either direction. There is a change. It's only the net result that seems equal. This is different than a static equilibrium that you may see in, for example, physics, where forces may balance out and cancel out, and so there is no net motion, but the forces are actually at a static equilibrium. There is no movement of the substance or of the, thing in physics that's supposed to be experiencing the equal forces, static equilibrium. In chemistry, we have dynamic equilibrium. Where there is motion, it just seems equal because the rates are equal and the concentrations are constant. Okay. Once you've established your equilibrium, you want to determine whether it is favoring the forward reaction or reverse reaction, because that's in turn going to indicate whether you're favoring the products or the reactants. So if in the end of the reaction you have more products, then you would say that the products are favored. If at the end of the reaction, the reactants are greater in concentration, you would say that that reaction favors the reactants. We're going to look at something called the equilibrium expression that's going to give us a quantitative indication about which one would be favored, the reactants or the products. So here is that equilibrium expression. This is a capital K, the first thing I want to point out, as opposed to the lowercase k used in the rate law expression. The equilibrium expression uses a capital K, and instead of looking at data tables to get our exponents are actually going to come from the coefficients. So this is why we're using this little format to show you how to set up your expression. The coefficients do become the exponents. So where little c was the coefficient to big C, in the formula I have big C to the exponent of little c, big D to the exponent of little d. So the exponents now are the coefficients. As far as the formula goes, basically you want to do concentration of products over concentration of reactants. So if C and D are my products, then I would have C and D on top. Where A and B are my reactants, I have A and B on the bottom. So I'm going to write my expression where K is set equal to products over reactants using the coefficients as subscript. Something else to note about K expression is that it varies with temperature. So remember this tomorrow when we talk about Le Chatelier's principle. Le Chatelier's principle is going to show shifts in equilibrium, and so when we do shift the equilibrium due to temperature, we are going to have to look at the change in K. But that's only with temperature. So you've seen K now in two different situations where it essentially represents some sort of constant. It's very typical for chemistry to use K as a constant, different subscripts to indicate what it is the constant of. You could use C for concentration, P for pressure. This is solubility product, acids, bases, lots of different types of K. The one that we're using today is Kc, the concentrations. So let's write an equilibrium expression for this example. First thing I want to write down is Kc equals. Similar to how you had to write rate equals, expressions have two sides. So we have to write Kc equals, and now I need to figure out what goes on the top. And I'm going to use my products. So I'm going to write PCl3 and Cl2. Those two things are going to go in brackets. I know that there is a plus sign in the equation because this reads we're forming PCl3 and Cl2, but the formula is multiplication. So do not include the plus sign when you set up the products on top. Now I want to put my reactant on the bottom. PCl5. Okay. Once I have product on top, reactants on bottom, I want to put the exponents in, which will be the coefficients of each substance. Since this equation is balanced with one coefficient for everything, one would be my coefficient for every single substance, and you don't write the one any more than you would write the one for a coefficient. So this is my equilibrium expression for this example. Simply putting products over reactants. Now let's try one that does have coefficients. So I'm going to write down Kc equals, and then I want to pick out my products to put on top. The products are NO and H2O. NO and H2O. I put those in squared brackets. And yes, it matters that it's brackets and not parentheses because we are going to be plugging in molarities for concentration here. So we want squared brackets. Then I want my reactants on the bottom, the ammonia, NH3, and my oxygen gas, O2, each in its own bracket. Now I want to input the coefficients as the exponents. So the coefficient for NO is 4, so I would put NO to the 4th. 6 waters, so raising H2O to the 6th. There are 4 ammonias, So it's going to be my exponent for ammonia. And there are 5 oxygens, so I will have 5 oxygens. So just taking the coefficients, putting them in as the exponents after you write product over reactant. Product on top, reactant on bottom. Always kind of backwards in chemistry. So this would be our equilibrium expression for the concentrations of this reaction. There is one small catch. Seems too easy, right? There's got to be something iffy about it. The phases do matter. The only phases that you would include in equilibrium expressions should be aqueous substances and gaseous substances, because those are the only 2 things that actually have varied concentrations. So since we're doing Kc, I only want to include things that would have concentration values. What we're going to consider is if I have a pure liquid or a pure solid, that concentration would just pretty much be like 100% pure copper or 100% pure water. So what does multiplying by 1 really do for us? Nothing. So we're not going to leave these things in the expressions. If they don't have an effect on the equilibrium, they don't belong in the equilibrium expression. So we're going to pull these things out. So if I looked at this same example, but using liquid water instead of water vapor, I would simply remove the water from the equilibrium expression. So this would be the correct equilibrium expression for the given equation here with water as a liquid. What we wrote a minute ago would have to be for water as a vapor. All right, so that's the one catch. Now let's try doing the actual math, plugging in molarity. Because of the brackets, I know I need molarities here. So let's look at our question. It says I have 1 liter of a mixture, and then it gives me individual moles of each substance. So if I have moles and liters, how can I get molarity? Well, remember molarity was equal to moles over liters. So for PCl3, let's do that one together, 0.172 moles over 1 liter. Dividing by 1, of course, doesn't change it. Missed my 172 m. Now, what you got to watch out for is if this says 2 liters or 4 liters, then you have to cut your given moles by that number of liters, because it should be in molarity, moles per liter, when you plug it into the question. Since this is all 1 liter, each of these moles can actually just be considered the molarity. Okay? So no division necessary on this one. So let's start plugging things in. Kc equals, my first concentration was for the PCl3. That's going to be 0.172. Okay. You do have to be careful that you're using molarities when you plug the numbers in. However, K does not actually have a unit. So we are not worried about the molarities canceling throughout here. As a matter of fact, half the time they don't cancel. That doesn't matter because K is simply a ratio. Think of it like a percentage. It doesn't really have a unit. So you want to have molarities in order to get the correct answer, but don't worry about tracking the units in order to get a unit for K because K doesn't have a unit. Okay, next was the chlorine. So the chlorine has a molarity of 0.086. because it is 0.086 moles per 1 liter. And then on the bottom, I'm going to plug in the molarity for the PCl5, which was 0.028. Don't forget your exponents. This was the one we did first where the exponents were all 1 because the coefficients were all 1. But if you have an equilibrium expression with exponents, those exponents would come into your expression, and you would have to treat that as if you were squaring that concentration or cubing that concentration, whatever that coefficient happens to be. In this case, the math is simply raising each of these to 1, working out the multiplication and division. So what do we get for our K for this example? There it goes, 0.53. So we want a when we want a numerical value for K, we plug in the concentrations, being careful to consider the exponents as well. And then we squash this all down to a decimal, plug it all the way in to get that final decimal answer. Whether that number is greater than or less than 1 is really what we're after here. So what does that number of 0.53 really mean? Well, if it's less than 1, like in this example with the 0.53, that would be the second one. If it's less than 1, like with this example of 0.53, that means it wasn't a super efficient reaction and most of the reactants remain unconverted. So this would be basically, we favor reactants. Whereas if K is greater than 1, maybe this was 1.53, that means it was a very efficient reaction and it made a lot of products. We would say then that it favors products. If K happens to be 1, that means that the concentration of reactant and concentration of product just so happen to be equal to each other. Do not mistake that for equilibrium. We're at equilibrium here with a Kc of 0.53. It just so happens that the concentration of the reactants ended up greater at that equilibrium, but those concentrations would remain constant. If you had the K of greater than 1, you're still at equilibrium. It's just at a different type of concentration ratio. If the Kc equals 1, that simply means that the concentrations happen to be equal at equilibrium. It is possible, but not necessary. So that's K. What kind of ratio of reactant to product do I end up with? We have one more expression called the reaction quotient, and it is very similar to K. So similar to K. K is going to be this ratio of reactant to product, the whole thing of putting product on top, reactant on the bottom, raising it to the exponent. When you reach K, when you calculate K, you're calculating that ratio at equilibrium. So actually, let me recap that formula for us with a marker that works. Kc equals product over reactant, where the coefficient is our exponent. The reaction quotient is the same thing. The catch is, it's just not at equilibrium. Or I should say not necessarily at equilibrium. So we're going to calculate Q in the exact same way that we calculated K. The math is literally the same. You're still going to put your product on top, your reactant on the bottom, raise everything to its coefficient. What Q is going to allow us to do is compare our ratio to the ratio at equilibrium, or the K value, and see if we happen to be at equilibrium, or if we need to have more of the forward reaction or more of the reverse reaction. Which direction do I need to shift in order to get to K? So Q is the same ratio, but not necessarily at equilibrium. If Q equals K, then I'm at equilibrium. If it's not, I need to figure out which way to go. So our reaction quotient is calculated the same, as I've said now a couple times, but it's just not necessarily the equilibrium concentrations. That comparison of Q with K is what it's all about. So if I have a Q that is less than K, that means I haven't quite reached equilibrium yet. And so I need more of a forward reaction. I need to favor my products. When I am at K, say you calculate Q and it happens to be the exact same thing as K, that's a verification that you actually are at equilibrium. But if you calculate Q and it's higher than K, you've overshot your equilibrium and you need to have more of a reverse reaction. You can go backwards and favor the reactants more. So it's all about comparing Q to K. All right, while I'm here, I have a super cheesy way to remember what to do. If Q to K, it's important that you have Q on the left and K on the right for my little trick to work. So I think of it as OK, even though it's really QK. And if it's greater than K, think of the little alligator trick. Remember from math class, we want to eat the bigger number? Well, now picture that alligator needing to walk towards K. So if it's open towards K, that alligator would need to walk towards K. So that means that we're going to shift right. On the other side, if I have Q versus K, where Q is greater. So now my little alligator needs to come towards me. It needs to go left in order to get to Q to eat it. So we would say the reaction proceeds left. So when I'm asking which way to shift, I'm looking for left or right, where right would be the forward reaction and left would be the reverse reaction. And in order to do this, we can literally think of the alligator needing to walk towards the greater number, and that's going to give you the correct direction. So, silly little trick. I know the alligator is kind of from grade school, but I like it as a little trick for Q and K. All right, so let's actually try a problem. So, we have here hydrogen and iodine gas forming this hydroiodic acid. It actually gives me the Kc of the reaction to be 49. So I'm going to write that off to the side here. Kc equals 49. Notice that they mention the temperature. Similar to in the solubility problems, they would always mention the temperature because it is dependent on temperature, but there's nothing that we need to do with the temperature for these problems. But it is going to stipulate it because K would be different at a different temperature. The next thing that it starts giving us are moles of all of the substances, which we have to be careful because we know when we write the equilibrium expression, we really need molarities. So we've got to watch out. How big is our container? We lucked out here. It's another 1 liter container. Keep in mind that if it were 2 liters or 3 liters or whatever, you would have to divide all of those moles by the liters so you actually have molarities to plug in. Now, let's start off with writing our Q expression. Q is equal to, just like K, product over reactant. So the product would be my HI. So I'm going to plug in bracket HI. And my reactants are the hydrogen and iodine gases, which I will separately put in brackets. Remember, this is just a notation that I have hydrogen and iodide. The math would be a multiplication, so there's no plus sign in between here. Once you have product over reactant, check your coefficients. 1, 1, don't need to do anything, but the 2 I'm going to need on the HI. Now I want to plug in the molarities. So again, be careful of the liters. So since I have 1 liters, the moles are the molarities. And the first one on top I want to look for is the HI. So that's going to be the 0.66. And again, I'm not going to write the units. I'm not worried about them canceling out. I just want to make sure that I have molarities when I put them in there. So that's my HI. So notice how that was squared. You want to make sure that you don't forget the square. It's probably the most common mistake I see with this. Then we have our concentrations of hydrogen and iodine here, and they happen to be equal to each other. So we need them twice. 0.22 times 0.22. So now we want to put this in the calculator. Don't forget to square the 0.66, and then you're dividing by 0.22 twice. What do we get for Q? So we get the 9. Again, notice how the molarities are in here. I never write them because a lot of times they actually don't cancel out. Here they would have, but a lot of times they don't. It doesn't matter. You do not want them in your final answer. So the Q is equal to 9. Now, what does that mean? So I'm going to use my little alligator trick. I'm going to write Q versus K. The Q is the number I just found of 9.0, whereas the K is what they gave me in the beginning. So what's greater, 9 or 49? 49. So if I'm opening towards the K, my alligator would want to eat the K. That's the direction the reaction will proceed, whatever direction the alligator has to walk. So that means we're going to shift to the right. And where I have reactant making product right, that would be the forward reaction. Again, the answers are usually looking for left and right, but I do want you to know what that means. And if I'm shifting this direction, that's now going to favor the products. So that means I'd be making products more quickly, and I can reach the equilibrium that way by shifting the equilibrium towards that direction. So it's all about this comparison from Q and tying it back to K to see which way we need to go to get to equilibrium. So if Q is less than K, we're not there yet. We need more forward reaction until we reach the equilibrium. All right, guys, that's going to do it for Notes B, all about equilibrium, calculating K and Q, and comparing Q to K. The next set of notes is Unit 10, Note C, which is all about Le Chatelier's principle, which will talk about a shift in the equilibrium. We'll see you there.